So, hello everyone. Thank you for joining. My name is Asif Usmani. I'm a professor of structural engineering at the University of Edinburgh. I have with me my student Jiang, who's going to correct me where I go wrong because he does all the real work. So let's start. We will talk about the background of this. I didn't tell you the title, so it was modeling of structures in fire using OpenSees. So I'll give you a little bit of a background of this, and I'll talk very briefly about the key features of structural behavior at elevated temperature. I'll talk about what we have done with OpenSees, the implementation of structures in fire modeling in OpenSees, and we'll present a few examples. And we'll also talk about the work that we have planned in the future. The traditional design of structures in fire is dominated by considerations of material degradation at elevated temperatures. So it's this is very much the consideration that people have in they think that it's key thing is that what happens to material, and when it gets to high temperatures, then it loses strength, etc., and seems to be the main consideration in traditional design of structure in fire. Because of that reason, structural members are protected from fire to delay heat transfer, limiting the maximum temperature in the member to an acceptable value over given fire duration, which is designed to be a standard, which is not really an actual fire. So all steel structural members are protected typically, but concrete structural members can typically, or concrete structures, concrete buildings can get away with just providing a little extra cover for say a longer fire to the reinforcement. This sort of approach, which is a prescriptive code-based approach, does not really account for the true behavior of structures in true or natural fires, in real fires. So this, to our mind, results in a dissonance, in a disagreement between load and resistance and demand and capacity. So this was first sort of brought to a seminal event that brought to the notice of the particularly the steel industry and structural engineers in UK when a building that was under construction in the Broadgate Phase 8 development in London in June 90 caught fire, and the building, most of the building was not fire protected at that time. There was a 4.5-hour fire with temperatures reaching over 1,000 degrees C, and there were pictures of damage there. You can see it. You can download a report about this in the given URL. So the total losses from this damage were about from the fire damage were about 25 million, but the structural repair cost was only about 2 million, and this was completed in 30 days. So this was a spur to the steel industry to set up with European funding and with collaboration of Building Research Establishment, and at the time it was British Steel, who got together and developed got together and set up these 4 large tests. Well, actually there were 6 tests, 2 tests by BRE and 4 tests by British Steel. Now it's Tata Steel, in fact, not for us. And this plan just shows the 4 tests that were carried out by the British Steel at the time. And you can download the report on those tests on the at the URL that's given at the bottom of the slide. So this is just a picture from one of the smallest tests, the strain beam test, which we did a lot of modeling to understand. We started working with British Steel in about mid-90s at the end of these tests, B meaning University of Edinburgh, and we did say this is one of the first models that we did in using software Abacus to understand the behavior of the Cardington fire tests. So the key lessons that came out of the tests and the modeling were that steel frame composite structures exhibited robust resistance in fires, even if the steel beams were left unprotected, because most of these tests that were carried out in Cardington had most of the beams unprotected. So as a result of that, in the late 90s, we got together with consultants like Arup, and we came up with new ways of designing, more on the basis of performance, designing structures, and these methods were used in real buildings in the UK, and the regulation accepted significantly reduced fire in some of those buildings. However, 2001 came, and we all witnessed this horrific event of the terrorist attacks on the World Trade Center, and that kind of made us think whether the lessons learned from Cardington were we had to rethink those. So we started looking at the collapses of the World Trade Center. We did some modeling work on that. Not in the way that NIST did. The NIST investigation was very much about a full forensic investigation, while our work was very much about just understanding what was different in these structures compared to, say, the Cardington structures. Why did they respond so differently? If it can be assumed, and that's what we assume, that fire had been a key factor in the collapse of these buildings, because they clearly had survived for a significant period of time after the impact. So this is just a few pictures from our early models. This slide shows one of the 3D models. Hopefully the animation would work. This is one of the most comprehensive models we developed, which showed us that in a multiple floor fire, a finite element model of the World Trade Center does show collapse. So in a sense, that kind of restored our faith in the work that we had done before in Cardington, because the models clearly showed what happened in Cardington as well. So a lot of this work can be found in references on whole building, whole structure modeling here. So if we look at now, go on to look at the behavior of structure members at elevated temperature, the traditional approach is, as I mentioned earlier, is just trying to determine the or trying to limit the temperature increase in a structural member. So you may put an isolated structural member in a furnace and check the temperature increase and how long does it take in a standard fire. But real structures typically would be not a simple beam. It will be more likely. It is more likely to be, say, a composite beam like that, with concrete and steel connected with composite action. You may have finite restraints against rotation and translation at boundaries. So we feel that the 3 key effects in the modeling must be considered in modeling. Obviously, material property changes due to temperature changes are important, and they must be considered. And another thing that we found is very important, particularly at low temperatures, is the thermally induced deformation. And of course, the restraint to this thermal deformation is the third. So these 3 are the most important issues that we model. So material property changes in structural steel can be obtained from a lot of code. So this is just an example of the kind of material property changes that you find in the Eurocodes for structural steel, and you can find similar kind of information about concrete. So this is the behavior of stress strain behavior of siliceous concrete at different temperatures. So if we now look at the behavior on those key things, based on so we talked about material properties. Now we are talking about the thermally induced deformation. So if you have a thermal expansion, say in a beam like that, simply supported beam, you can obviously assume that this will sort of, see that it will expand in this way if it is just a mean temperature increase, and you can obtain the strain that is induced in the beam because of that increase in temperature. You could also have a through depth thermal gradient in the beam without having, say, a mean temperature increase. Now that's realistically not possible, but it's not a realistic thing. But just for argument's sake, just theoretically, trying to understand the behavior of thermal gradient, you will have something like that happening. So your beam will have some curvature in it, and then you can, and that curvature is given by that formula there. Alpha this is the coefficient of thermal expansion, and T comma Y is the gradient. And you can determine that shortening of the beam or the movement of the support towards the left through that formula if you wanted. But what happens in real structures, of course, these two things happen together. You have some mean temperature increase and you also have a thermal gradient. So what we find is because the two are moving the support in different directions, we see that you can get large deflections in structures, but those large deflections do not necessarily mean that the structure has too much damage in it. So it can be those large deflections misinterpreted as, which has been perhaps the case in the past, misinterpreted as damage. So these things, of course, are also affected significantly by restraint. So if we remove Bowler and put lateral restraint and increase temperature to delta T, then you would have the beam yielding at a certain point, or the beam is slender, that it would buckle. You could also have restraints like that. You can have the thermal bowing also restrained, not just thermal expansion. If you have a thermal gradient, that will give you a uniform moment across the section. And of course, more realistically, you have this sort of restraints, and you can write formulas for that too in terms of how the structure responds, what would be the moment in it. So there are again a lot of papers about this stuff that we have written, and these can be found in some of these references mentioned here. So we have recently become interested in looking at the effect of fire following an earthquake. So looking at the effect of, so if the structure is damaged by an earthquake, what happens if there is a fire? So this was done in collaboration with India. We did some tests on a frame in the Indian Institute of Technology, Roorkee, in collaboration with them. And so this is the frame that was built, and it was damaged using, you can see the picture of the jack there, which applied a cyclic loading to it, to the frame, and it caused some damage. After that, we put some holes around it to make a compartment, which was then subjected to a liquid fuel kerosene fire, causing flashover fire there, which we could keep on burning for as long as we wanted with a constant fuel supply. And this is the structure after the fire. So there are, and again, some of this work has been published, and you can find the information in papers. So that is the start of that work, and even before that, we became very interested in OpenSees as a potential platform where we could, because we had so far been working with Abacus as a commercial package, but we find that because of the limited way we can interact with it, it's difficult if we wanted to really model real fires, such as localized fires or moving fires, which will give us considerable variation of temperature in terms of the space and time. So if you have moving fires, clearly there's a lot of variation in temperature. Even if you have a localized fire, there's a lot of variation in temperature. And this can be very tedious in a commercial package, in putting all that data in. So if we thought that if we could put some heat transfer code into OpenSees and are able to automatically do this, then we will sorry, the phone rang. We'll turn that off. Thanks. Okay, so we feel that OpenSees offers a possibility of linkage with OpenSees offers a possibility of linkage with OpenCFD packages to model the whole problem, and it also offers the possibility of multi-hazard modeling, as we mentioned, fire following earthquake, and of course the other kind of advantages that we have with open source software, such as developing an international community of researchers that collaborate across boundaries using common computational tools, and the advantages that you have in terms of software robustness, longevity, sustainability, etc. Lenin, can you take over? Yeah. So the OpenSees development work at Edinburgh is Leeming, my student, will describe here.
Hello, everybody. I'm just here to introduce what we did in the OpenSees framework to bring the structured fire dissemination capabilities into. And as we know, to carry out the analysis, we need the material classes and the section classes and classes and the load, which is the summer action, and they would develop the fire load pattern, which could just using allow us to use a lot of summer action loads and so for the material classes, we developed the Steel 1 summer, and as we know, the Steel summer materials and the concrete materials. The Steel 1 summer is based on the Steel 1 with temperature-dependent properties defined, which we actually just bring the temperature-dependent properties from the Eurocode for the structural steel. We have a lot of reduction factors could be applied on the yield strengths and to the tangent modulars. And the teacher comment for the Steel 1 summary is exactly the same as the Steel 01 in the OpenSees framework, which has which existed in this framework. For Steel 02, it's just has a kind of a smooth from the elastic to plastic stress strain curve, and it's also based on CO2 with temperature-dependent properties, which is also the structure steel in the Eurocode and the TICO command, as we see just a slightly different, like compared to the Steel 01 summer. And for the concrete 02 summer, it's also it's quite similar to the concrete 02 in the OpenSees framework, but we just didn't have to get the summer elongations, which just account the expansion of the fibers and the reduction factor of the stiffness, which applies on the tangent modulars. And for the beam elements, we have to use the fiber section 2D summer, which works as a section class. And it's also based on fiber section 2D. We develop the functions defined for which are defined for constraints, the summer strains, like the summer elongation, and the trial strain will reduce, will subtract the summer elongation, which is the summer strain. And we have the interface to the loader class, which is beam to the summer action, to get the temperature-dependent properties, and we have the transferring. We have to transfer the temperature data to material models, which is defined in the Steel 01, Steel 02, and concrete 02 summer. And the TICO command for fiber section 2D summer is a little bit just similar to the fiber, but just the keyword, the identity word is a little bit different because we have the fiber summer. And for defining the fibers and bring the fibers into section is the same, just to use the fiber command of patch or layer, which could be find a reference from the OpenSees website. And as you see that We have for the 2D beam 2D summary action, for the fiber section 2D summary, that's this thing, and define the fibers, bring the fibers in, and like the conflict section, we have that could use the patch commands to define the fibers. But in the 2D analysis, it works just because we ignore the Z coordinate that works just like the equivalent fibers along the y-axis. And so far we have the beam element, which is this beam connected to the summer, and actually we have the 3D version, which doesn't been just updated in the Berkeley website, the exactifier, but we have the updates on our wiki page. This beam connected to the summer is based on this beam connected to the, and we could constrain some stresses and the resisting forces. When calculating the resisting forces, we just have to account the summer stress, which because of the summer elongation. And we have an interface to load cost beam to the summer action, and transferring the temperature data to fiber section to the. Actually, the temperature works like just, so from the beam to the summer action, even earlier, just like the fire load pattern, we have the beam to the summer action define the temperature data, and the temperature data will be transferred from the beam, this beam connected to the summer element to the fibers, and the fibers will find out where the fibers are in the temperature zone, and to get the temperature, the real temperature of the fiber and the fiber, just the temperature data, and the material will respond to that. It's going to be a temperature dependent property. And the typical command is a little same, just the element is just being called summer. We update the keyword for this command. But the other arguments are the same, so the element tag and the load and the number of integration points, so it's the same. But as they point out, this is the temperature data is defined by the beam to the summer action, and it goes to this beam connected to the summer element. And for each integration point, we have the fiber section, and the temperature data where goes to the fiber section to the summer, and we'll find out the real temperature of each fiber and the fiber, and then we get the location of the fiber and the area and the map tag and the temperature, and just to specify uniaxial material which has the summer properties. For the beam to the summer action, which actually is a load class, and could co-works with the load pattern, fiber pattern, or plane pattern. Plane pattern, which allows us to use the linear time series, which could be quite easy and simple. For fire load pattern, we can define 9 time series, which could work as on the beam section. For the beam to the summer action, we provide 9 data points, but you don't need to use to define the summer action with 9 data points. We have just a facility like 2 data points or 5 data points, which make a simple command. So if you just want to use a linear temperature gradient, or maybe just a uniform temperature, which allows you to just only 2 data points and 5 data points, maybe just a detailed temperature distribution along the section. And actually, definitely can use the 9 data points. For it's just the 9 data points allows us to build 8 temperature zones along on the section, and for the fibers each temperature zone, and we find out just we get the temperature of the fibers, and it depends on the location of the fiber, and we just make the calculation.
If I can interject here, I mean, sorry, I had to run away to look at something else. We are really this is one of the advantages of using OpenSees, because it allows us to define all these things ourselves. Like in Abacus, we have problems in defining the very steep thermal gradients, which would normally exist in sort of, say, concrete members, because it only allows like 3 data points or 3 temperature points by default. So these sort of things are very important if you really want to model real behavior. And so at the moment we have 9 data points, we assume we think that this is enough. But if we find other cases where we need more, we can certainly add more. Okay, you can carry on. You did a good job.
Thank you.
Yeah.
And for the we have the fire load pattern, which we're covered with the time series definition and the past time series, and you can use the linear time series. Which the advantage of this fire load pattern is just we have 9 time series on the section, which can define 9 temperature time curve for the section for the summer action load, and for the plane pattern actually we just have a linear linear time temperature curve. But here we have 9 time series. It's quite a big advantage of this, and we provide an interface to the summer action. We generate a vector of load factors. We have the vector with the size of vector with the 9 load factors in, and the fire load pattern have the 9 time series. For each time step we have 9. It's just specified load factor, and the load factor will times to the maximum temperature. So that's just we are quite free to define the specified summer action of the temperature load. Here, yeah, we could use the past time series, and for the past series we have the time and the value for defining the past, and we could just use the beam summer and the yearly loads, just the element load, and to define the temperature. We can use, as we just mentioned about the beam summer action, we could use 2 temperature points on 9 or 5, so whatever. And
so this is also very important in the same way as the thermal load that we talked about earlier, because the section could be over the full length of the fire, from heat to cooling stage. You could have sections which are even at cooling are actually heating, and other sections that may be cooling. So you really need a full definition of all these points over the full length of time of the fire that you want to model. So this fire load pattern command allows that.
Yeah, we can define a temperature time curve, which is what we want for the fire stuff. And it goes to, okay, now it goes to the examples.
Okay, you can carry on. Yeah, so the first example that these guys have tested, this is just for this seminar to just show the sort of key features of behavior, and also the kind of things that can be done with OpenSees. A lot can be done than we have actually shown here, but we're just showing some basic examples that could be good ones to start with. So we start with supported steel beam with defined uniformly distributed load, and at the moment just apply a uniform temperature rise and some sort of time series or a path defined time. Yeah, and that's shown in the figure on the right. The temperature time is defined, and this is analyzed. So this model is available on our wiki page. So these are the results of it. So if you look at the mid-span deflection beam, that's the figure on the left. That shows the kind of expected behavior that you would get. So the mid-span deflection, if you only have material degradation happening, because there is no UDL, there is no load on the beam, there is no deflection. If you also model thermal elongation, still it's the same picture. There's no there is no deflection. But if you add a UDL, then you see that the UDL is the displacement is different for the case where you have thermal elongation or no thermal elongation. So that shows you that the kind of important factors that must be included. Then look at the displacement of the free support, then you can see the same thing, same four things with material degradation and elongation, material degradation only, and with UDL, without UDL. So you see the curve with the blue curve with the triangles.
Yeah.
Has initially positive displacements, and then as the UDL causes the beam to deflect, then the support moves back and goes beyond its initial position, and then it kind of stabilizes. If you do not model the thermal elongation, then of course the support does not move to the right at all, and it just deflects, which is what you'd expect. So this is the second example, which is also very interesting, which shows just a beam, so you could just see it, or even a column or a bar problem, where you have one side of the bar heated and the other side, so between node 1 and 3, the element 1 is heated, while the element 2 between node 3 and 2 is not, we basically run this problem. We can the useful thing about this problem is that we can write this whole solution analytically. We can solve the only degree of freedom is the horizontal displacement at node 3. So we can write full analytical solution, and this is just showing you the result from OpenSees, but we can do the same of the movement of this node U, which shows an interesting behavior. The node is initially pushed towards the right, and then it comes back because of the thermal expansion. It comes back. This is material degradation happening and the stiffness loss happening at high temperatures in the heated member, and the elastic member on the other side then pushes the member back, pushes the node back, and so this is an interesting benchmark test. At the moment, we only have this as stiffness degradation, not the yield strength, which is not bringing plasticity in, but we can do that as well, and that can also have an analytical solution, and also it allows us to check the nonlinear material behavior, including nonlinear, say, geometric behavior here. Okay, so this is another beam example with the elastic restraints at the end of a beam. And here we can apply these translational stiffnesses or rotational stiffnesses, with, and we can look at the, based on the different values of these displacements, the effect of restraint, right? So as I said earlier, the restraint is a very important effect. So of course you can vary these stiffnesses from 0 to infinity, which means fully fixed. So we can have, so there's a paper in which we have looked at this problem, which shows lots of interesting solutions. Here we just show the solution for some, I'm not sure what the exact value has been chosen in this, but you show, oh, it's here, yeah, the elastic translation rotation stiffnesses are shown here.
As its temperature is rated and the stiffness, just to have the stiffness degradation. So that's why the horizontal load is
That's right. So this one is the horizontal displacement at the roller end, and it shows initially the beam is pushed out because of the expanding beam, but as the temperature goes up, the beam loses stiffness, and this stabilizes or comes down a little bit. Then mid deflection does something else. It goes initially straight line to a maximum value, and then it returns back. Then it returns back to the stiffness. Yeah, that's right. Okay. Okay, so that's the third example. Another very important example that we always test is of composite beams, where we have steel and concrete, say, composite, and we use two methods of solving it. One, we assume rigid links between the steel and the concrete, and another one where we assume a single section. Actually, the figure is misleading because both sections are taken as exactly the same. So there is actually a gap in the second section as well. And so you've got these the syntax for the TICO file defined here. And if you look at the results, then you get the deformation shapes as we expect. And if you look to plot the nodal displacement, the midspan displacement, midspan vertical displacement, then the two models, the rigid link model and the single section model, give slightly different results, which are expected because the rigid link model has well, rigid link model allows the rigid link model is more constrained because it enforces all the degrees of freedom to retain the same value, which is slightly more constrained than the single section model, in which you can assume that over the section depth you can have, say, different horizontal displacements, etc. So it shows slightly higher displacement. So that's all the examples that we thought would be appropriate for this. We may want to look at more detailed examples of 2D frame modeling to collapse and 3D beam and shell frame models, which we are working on. We also have completed heat transfer analysis with OpenSees, but we have not been able to offer that offer the TICO based interface to it yet, and we hope to work on that with the help of Frank and OpenSees people in California. And you can because you know, we've noticed that some in the last version that was released of OpenSees, we found some bugs. So we have updated those on our own wiki page, where the URL of that is given. You can download the bug-free version there. We'll talk to Frank and update the Berkeley version. And we are currently working on developing. Well, these elements exist. We want to develop this shell MRTC4, which is available in OpenSees, a kernel version of that, to allow full 3D modeling of full modeling of 3D structural frames, including the slab, because the slab behavior is very important. It may not be so important, say, in earthquakes, but it's very important in fires. And we're also looking at different new section models working with shells, and we're also looking at new versions of material models that are available in OpenSees. This is just the full. This is the heat analysis classes showing heat transfer and fire classes that we've developed in OpenSees, and this works, and it gives us this sort of results. So you can model these sort of 2D and 3D heat transfer, and that's all. Thank you, Frank. I hope that was okay.
That was perfect.
And everyone, thank you for attending.